Virtual assistants are now more popular than ever. Most of the virtual assistants on the market allow the user to interact with it through natural language, whether it be audio or textual commands. The virtual assistant then processes the input query and provides a response in natural language as well. We believe that certain responses are better suited for visual than a textual display. For example, if you ask your virtual assistant to fetch your 5 newest emails, wouldn't it be nice to have the emails displayed on a nicely formatted GUI instead of being read aloud to you? Recently, researchers at Stanford developed Berceau, a graphic virtual assistant that can automatically convert natural language commands into a GUI that can display the response. Berceau has been shown to be successful and well received by users, but it is reliant on a pre-built template database designed by humans. In our project, we seek to expand on Berceau's capabilities by allowing it to automatically generate new template layouts. We present Exhibit for Berceau, a neural network model that is trained to generate new UI layouts given a specification of the components in the UI. To accomplish this task, we data mined RICO, a large data set of GUI images and their associated metadata. For us, the most critical information from RICO is the location and bounding boxes for the individual components. We process the RICO dataset and extract information about the components. Then, we use k-means to generate clusters of similar components. We label the components by the cluster that it was assigned to. With the labels, we build a discrete vector representation for each UI in RICO. This discrete vector is simply a list containing the number of elements from each cluster present in the UI. We use this vector as the input to our neural network model. The output of our model is a matrix of pixels. The elements of the matrix correspond to the label of the UI element at that pixel location. With our input and output defined, we use a fully connected neural network to transform the input component vector into an output pixel matrix. To train the network, we optimize the network parameters to minimize the mean squared error between the generated pixel matrix and the ground truth pixel matrix. Here are some of the examples that our models produced. Thank you for watching our presentation of Exhibit. We are happy to take any questions and feedback at the poster session.